Okay, as Steph said, my name's Terry Odgers. I'm from RedDog Scientific Services. We were established in '95 and we supply equipment. Those are just some of the agencies that we represent, but more importantly the types of equipment, borehole logging. You guys can all read, but it's very quick. The one that we're going to cover today is GSSI ground penetrating radar. And as I said, I'm going to go through these fairly quickly so we don't lose time hands-on. Does this one work?
Probably crash my computer. Sorry. No.
Oh, do I have to?
No, I don't think you would.
Excuse me.
Okay, sorry.
Right, so this talk was originally titled Geophysical Opportunities in Geotechnical Fields, but it basically covers what we want to cover today in relation to the utility scan system that you have here. Okay, this just goes through some shallow geophysical methods. We all think it's nice and sexy to go out and discover the next zinc deposit and have a massive mine built where you did your thesis or whatever. But the reality is most geophysicists end up doing slightly more mundane things, unfortunately. And there's a lot of opportunity these days to branch out into the shallower fields. And again, ground penetrating radar is one of them, but there's things like surface wave analysis, seismics, some very nice stuff coming out with high-res magnetics at the moment, some really cool drone applications. And then obviously electromagnetics as well. There's a lot of work going on in the groundwater exploration field at the moment. Okay, for ground penetrating radar, one of the advantages are very rapid data collection. It's the highest resolution of all the geophysical or remote sensing methods, or let's say geophysical methods. It's relatively easy to interpret. You don't have to have a master's degree in geophysics to do it. You can actually train a person to do it in literally a couple of hours, certainly to get clean data, good data. Obviously, like anything, it takes experience to learn what you are seeing and what's real and what's artifacts and so forth. But it's relatively easy compared to things like refraction seismics and EM for sure. The one limitation is that it has a very, very shallow depth penetration. I've got you at 25 to 30 meters. There are manufacturers claiming now with certain antennas and certain digital data processing, that they're able to see down to about 120 meters. Yet to see any good data or reliable stuff from that, but certainly the field is changing, so hopefully we will be able to see deeper and deeper as technology allows us. Basic elements of a GPR system, essentially very, very simple. You just need a console or something to generate the radio frequency signal. You need to be able to display the data and store it. And in that case, in the case of your system here, it's a SIR 4000 console. You need an antenna to actually transmit the signal and to receive the returning signal. And then you need some cable or Wi-Fi or something to connect the two. Sometimes you get units that are all in one, and obviously you don't need stuff like this. And then there'll be accessories, carts, software, that type of thing. But those are all just peripheral to the real, the actual method. So just going through this quickly, we transmit, as I said earlier on, we transmit in the megahertz to gigahertz range, which basically sits down right in the radio frequency band, and it overlaps microwave radiation. And our cell phones sit down here as well. So certainly not with this one, not with this system because of the frequency of the antenna, but if you use higher frequency antennas for concrete scanning, as you were watching earlier on, you would want to have your cell phone either switched off or away from you, because there will be interference. So basically what we do is we send some radio frequency energy into the earth, and it reflects off of targets or interfaces, and we record those reflections at the surface. So what exactly do we record? We want depth in general we want depth information out of a radar signal, but we can't directly measure depth. So what we measure is we measure the two-way travel time of the radio wave, and importantly that it's two-way travel time, so every time we do a calculation we'll either be dividing by 2 or multiplying by 2, because we send the signal out when it bounces back and we know the time that it takes to get here. The second thing that we measure is the amplitude of the reflection. So you get different, you can see here, much higher amplitude reflection and same reflector, but much lower amplitude reflection. And that tells us something about either the target, or it tells us something about the material between us and the target. So we can get information out of that. And then the third thing we look at is the phasal reflection. So we put in, it's not possible physically to put in a sharp spike of energy. So we actually put in what we call a triplet. So you send in a positive pulse, a negative pulse, and a positive pulse. And everything you record is a mirror image of that triplet that you're sending in. But occasionally you'll get a phase change. Sorry about that. You'll get a phase, every now and then you'll get a phase change, and that actually tells us something about the material that we're working with as well. And I'll go into that just a little bit later. So those are the three things that we actually record and we take note of when we work with radar. So radar, unlike seismics, where seismics is a measure essentially of the changes in density of a material, we look at electrical properties with radar. And the two things that concern us are the conductivity of the earth or the medium, but it's normally we're working on rock or sand soils. So we need to know a bit about how the electrical conductivity is going to influence us. And then we work with a property called the dielectric constant. So just in terms of conductivity, everybody knows conductivity. It's a very simple concept. And in an Earth situation that is primarily controlled by the water content and the clay content of the soils or the rock. And if we have high conductivities, it makes it very difficult to get radar wave penetration into the Earth, so our depths are limited. We still get very good information to the depth that we can penetrate, but the depths themselves are limited. And that can be sometimes quite severe, especially when you start getting into clays and decomposed shales and stuff like that, that have high clay content and may contain water as well. So that's just something to bear in mind. It's a nice little chart to bear, reference chart. And so if you're out working and you have a look at the soils and they're bright red and you rub your hands on them and they stain your hands, then you know there's a clay rich, and you can look at it and say, okay, this is going to be a difficult job or not. You know? The second thing that we're interested in is the dielectric constant, or sorry, the dielectric, and it's actually known as the relative dielectric permittivity, but the easier word is dielectric, denoted by the symbol epsilon. And it's a dimensionless measure of the capacity of the Earth or a medium to store charge as opposed to conducting charge. The value ranges are very specific. It ranges from 1 to 81, with 1 being air, where the radio wave travels the fastest, so there's the least impedance to it, and water being 81. You'll see that, I'll show you a table in a few seconds, there's no steel or metal in the table. And that's because metal is a true conductor, so it doesn't have a capacitance or doesn't have a dielectric. But in the scheme of things in terms of radar, metal can be considered as having an infinite dielectric. In other words, no radar signal penetrates it, it all gets reflected, which has some interesting repercussions for working with radar. And so, as I said, unlike seismics where we're looking at density changes in the material, we're actually looking at dielectric differences between the two layers of the Earth, for example, or between the Earth and a sewage pipe, for example. And it's those differences, the dielectric difference, that causes the reflection. So it's not a density difference, it's a dielectric difference, but very often the two correlate, because the material changes, so the density may change, and the dielectric changes by correlation. Strength of the reflections, they're just controlled by the difference, the difference in the dielectric. It's governed, the reflection strength is governed by this equation, epsilon 2 minus epsilon 1, sorry, the square root of epsilon 2 minus the square root of epsilon 1 over epsilon 2 plus epsilon 1. Now you can see if these two are very, very close together, that top, the top of that equation goes to 0. So basically then R tends to 0, your reflection strength tends to 0, and you can't see the changes. So what we want is, in an ideal world, a very large difference in dielectric between the host medium and the target. Then we get really nice bright reflections, and life's good. Unfortunately, it doesn't always work like that. In fact, it seldom works like that. The second thing that concerns us working with radar is depth of penetration, because we have such a limitation on our depth penetration. And that's, as I said earlier, governed by the water and clay content, and sometimes conductive contaminant. Now that can be leaking pipes, that can be forecourt of a petrol station, we have leaking bowsers, and there's a few other things, backscatter through backfill of building rubble will give you backscatter, it makes it a bit difficult to see. But these are things that we can't change. The one thing that we can change is the antenna frequency. Now the deeper, the lower the frequency antenna that we use, the deeper the penetration. And that's because of basically frequency dependent attenuation, and essentially high frequency waves excite the material more and are absorbed more readily, and so you don't get deep penetration. Low frequency waves, like a wave on a beach, tends to wash past the object and be reflected off a linear interface, and makes so you actually get energy back and you get information back. So that's one effect of antenna frequency, is depth of penetration. The second thing is a higher frequency means we have higher resolution. We can see smaller objects. So it's always a trade-off between depth of penetration and the resolution that we desire. And so some antennas have been developed with multiple antennas, multiple frequencies in one capsule. Then we've developed, or GSSI, for example, have developed certain antennas that are specific for an application, like a concrete scanning antenna. This antenna has a very wide range of applications, but we have some other antennas. Our dual frequency one is more specifically for only looking for utilities, for example. In terms of talking about frequency on antennas, so the antenna that you guys have is a 350 megahertz antenna. And when we say it's 350 megahertz, we talk about the center frequency of the antenna. So that one is 350 megahertz. And the center frequency is basically where you get your peak power out of the antenna. Now, just as it's not possible to put a single spike of energy into the earth, it's not possible from an antenna such as these to radiate a single frequency. So we actually radiate, we transmit energy. For example, this is 120 megahertz here, center frequency, and you can see on the power spectrum here we creating energy from probably around about 25 megahertz all the way up to about 250 megahertz. Hi, Sue. So we actually get a broad band spectrum. The second thing is, and I don't have a slide to illustrate that, the second thing is that the Earth acts as a low frequency, a low pass filter. So the Earth, in a lab you might measure a antenna as being 120 megahertz, for example, but by the time you've looked at by the time you've recorded the data, if you look at the power spectrum of the data, you'll find the whole bandwidth, the whole center frequency would shift down into the low frequencies, and the amount of shift depends on the conductivity of the Earth. But nominally we would rate these by the center frequency as determined in the laboratory. Okay, one of the things we need to know is our horizontal resolution. When can we distinguish two objects as opposed to only seeing two objects appearing to be one object? And that's just determined by the radius of the first Fresnel zone. So you guys have, I think, all done physics, so you've done this a lot more recently than I have. But basically, you're looking at where you get constructive and destructive interference from the radio wave transmission. And the important thing to know is it's depth dependent. So R0 here is your depth to your target. You can see as your frequency increases, your Fresnel zone decreases and your resolution increases. But as your depth increases, so your Fresnel zone radius, so your Fresnel zone increases. So this is one of the issues, is that as your radio wave penetrates deeper, or your target is deeper, the target essentially has to be bigger for you to be able to see it. Otherwise, you just physically don't image it. I use an analogy of the wave washing up onto a beach and you're standing knee deep in the water. By the time the wave gets to the shore, there's no evidence that you were ever there. And that's exactly that same thing. The Fresnel zone gets so big, it just doesn't see, you can't image the object. This is just, I'm not going to go through the table, this is just a table showing you the typical depths versus diameters of something that you would have to, the target would have to be able to see it. But there's one rule here, and it's a very, very basic rule of thumb. They called it, it was called the 1 inch per foot rule in imperial times, but I'm sure most of you don't know what a foot is. So it's about an 8.5% rule. The diameter of the object must be 8.5% or greater than the depth to be able to see it. It's not a strict rule, but it's a good rule of thumb if you're designing a survey and you want to see if you have any chance of actually seeing the target. This is a little less important to us in terms of radar work, because we tend to be looking for individual targets as opposed to thin layers. But essentially, your vertical resolution can be estimated by this, so it can be resolved by this equation. And the important thing here is to see that it's dielectric dependent and frequency dependent. So the higher the frequency, the smaller this term. So in other words, the thinner the layer that you can distinguish, and the higher the dielectric, the thinner the thin layer you can resolve. But as I said, this is not normally a big concern with us in radar work. Early on, I mentioned the polarity. So basically, what we're doing is we're putting in a triplet, and everything we measure will be a mirror image of that triplet. So here we have a single target, and you can see we have the first positive peak, the first negative peak, and then second positive peak coming back to us. And they're all being reflected off of a target that sits approximately in the center of that first positive peak. But occasionally we do get a phase change. And what the phase change tells us is that the radar signal has traveled from a high dielectric to a low dielectric. Right? So that's useful when you want to identify a void, for example. So a void, an air-filled void will have, in general, well, an air-filled void will have a lower dielectric than the host medium, so you should get a phase change. Sometimes they're very difficult to see, but in terms of, this is a very good example, concrete, with this will be probably, let's say, the first floor of a building, and it might be a parking garage underneath here, and you get a beautiful phase change at the boundary. They're not always this good, and certainly in a situation where you're looking for a void, like let's say a sinkhole type of environment, you don't get nearly as good data as that, but you do get that type of signature. And these are rebar, this is rebar in the concrete, and you can see what beautiful positive, negative, positive reproduction of the input signal you get. You know, really, really nice hyperbolas. Okay, and as I said earlier on, almost all the time what we want to do is we want to estimate depth to a target. Radar's extremely good at locating stuff and finding depth to it, not so good at telling you what the target is. and certainly not any good at telling you anything about the density of the material. So what we want to do is we need to convert, we are actually measuring two-way travel time. We need to be able to convert it to depth. And there's a couple of ways of doing that, a number of ways of doing that, sorry. First one is we use a standard dielectric table. Now, the velocity of a radio wave in a medium is related to the dielectric of the medium. It's proportional to inversely proportional to the dielectric of the medium. So if we know the dielectric, we can then, if we know the dielectric accurately, we can work out the depth accurately. The problem with dielectric is being largely dependent on moisture content of soils, for example. We can't do in situ testing of dielectric. You take it to a lab, and even then it's only really, it's got to be treated very, very carefully, and it's only really good for that very specific area. So it's not a practical way of doing it. But we do have tables that are built up empirically, so you can actually use these tables as a first guess, basically. So this is how you would calculate the depth, basically. So that's the wave velocity, c is the speed of light, and that's your dielectric, and so you can see it's inversely proportional to that. If we can guess that accurately, we can work out what the wave velocity is. That's all we need to do. Once we have the wave velocity, we can work out the depth just through the two-way travel time. Unfortunately, as it says at the bottom here, it's always only a guess. We have some tables. Air at the top here is value 1, water at the bottom, and basic things in between. But if you have a look here, for example, concrete's a good example here, a relatively narrow range, depending on the maturity of the concrete. Asphalt, also a fairly narrow range. But if you have a look here, soils and sediments, because soils tend to contain variable amounts of moisture, their dielectric can vary from very low dielectric, let's say 4, up to and higher than 30. Higher than 30, you don't get very much penetration, so anything sort of up in that area we don't normally work with. The one factor to notice here is that because water has such a high dielectric, if there's a water-filled pipe or a water-filled void, they're very easy to spot. They stand out like a sore thumb, so I'll show you some examples probably just now. The second one is using the shape of the hyperbola, but before I get into that, just need to go into why we see a hyperbola from hyperbolas in our data. And either a spherical or a cylindrical target will plot as a hyperbola on our radargram. And the reason being is that we don't know where the energy comes from. We are transmitting energy in all directions when we transmit the energy. Reflections come from in front of us, some come from behind us, some to the sides of us. And so by default, we plot the returning energy directly underneath the antenna. Sorry, that's the antenna up there. So if we're doing a survey from left to right in this diagram here, we would be way off the target. Sorry, the blue thing's the target. The energy would travel ahead of us, reflect off the target, and be recorded. And let's say it takes a time of t2 to return to us. We would then plot it directly below us. And because t2 is longer than t1 and t-min, which is when we are directly above it, we will plot t2 deeper on the radar section in time. We're plotting time here. And as we get closer and closer to it, the move out is hyperbolic, and until we get to directly over it, the shortest time that we can record, and the same thing as we go away. So this is why we see hyperbolas in our data from either diffraction. So if you have discontinuous layering, you'll get partial hyperbolas anyway, and cylindrical, and pipes are great examples of this thing. Those are 3 storage tanks in a forecourt of a petrol station. Anyway, so what we can do is we can use this shape. If we know the shape of the hyperbola, we can then use its eccentricity, or its flatness, its measure of its flatness, to determine the wave velocity, And once we know the wave velocity, we can then calculate the depth too.
Just a quick question on the last one. Are those multiples underneath? On the bottom
There or there?
on the bottom diagram.
Oh, sorry. Oh, those there.
Yeah.
Yeah. So what happens is, this is a fairly Sorry, these are two different sets of data for a start. I must just point that out. The bottom data, I just expanded so I could actually fit the diagram in. So it's expanded in the XY plane. But this is actually a very shallow PVC pipe with water in it. Sorry, no, this is not a PVC pipe. This is a cable. And what happens is the metal in the cable actually acts as an antenna if it's close to the surface, and it starts to radiate energy, and then you get these multiples that they'll ring all the way down through the data. So yes. Yeah. There's I'm not sure in the slide session if I've got a good example of that, but I do have examples of that. And that's, earlier on I said that metal has some properties which make it quite unusual for radar, and that's one of the properties. So it's one way of identifying the difference between, let's say, a water-filled PVC, shallow water-filled PVC, and a power cable. A power cable will give you those multiples all the way down through the data. Right, so we've gone through the slide. So basically what we're looking at is how to determine the shape of the hyperbola. So I pulled this out of this time delay paper. These guys didn't develop the method, but I just found this was a nice, what I thought was a relatively easy way to derive the hyperbolic, or to get the depth out of the hyperbolic equation. The important thing is we're talking about a homogeneous medium here. This can be, and in fact in this paper they expand to multiple layers. The maths gets quite tricky. It's quite intensive. This maths is relatively simple for you guys, not so much for me anymore. But basically, when you're dealing with the inverted vertical axis portion of the hyperbola, that is the part of the hyperbolic equation that describes it. I'm going to go through this very quickly, but x is A and B are the two axes of the hyperbolic equation. And here x0 and t are the depth and the offset at any point along the hyperbola. But basically you can go through the maths, and in the end you can solve for either, you can solve for the velocity, and from the velocity you can get the dielectric out, or what we really want is the velocity. So over here you can actually solve for the velocity in this equation here. Their paper goes, this is only just the intro to their paper, but I referenced it purely because it's the polite thing and correct thing to do. But it's not their equations, as I point out. So from the shape we can actually work out. So on your radar system you actually have a template that you can go in, and you can then, you basically fit a template to your hyperbola, and then the software on board solves for the velocity using this equation essentially. So that's basically using purely the shape. The third way to do it is using migration, and you also have that built into the software on your system. So this is what I said when I did my thesis. So you do this overnight. Now you slide a slider up and down with your finger, and it does it in real time on probably more data than I was working on. But basically there's numerous methods of migration, both time and depth migration, and then each one has a whole lot of different implementations. But essentially all of them in the end allow you to create a velocity model. Once you have a velocity model for your section, you can then place all the energy in the hyperbola back at the origin where it came from. And so whether you're using Kirchhoff or diffraction migration or FK migration or whatever, ultimately you take hyperbolas that look like that and you collapse them to their origin, which hopefully looks a bit like that. Now, what happens is if you use the incorrect velocity model, you can see this is probably a reasonable example. You can see this is an example of over-migration where you've basically taken energy from down there and you've moved it up to there. You've taken energy from down there and moved it up to there. So that's incorrectly migrated, and the reason is because this Earth is not homogeneous. But the parameters that I used for this were actually very, very good for these two pipes up here, or this section of Earth between there and there. And you can see those have resolved almost perfectly. So you'll never get to, there's another one that's over-migrated. You'll never get a correct migration section, but there are algorithms and there's software, not on board this system, but there's software that allow you to do a multiple layer model basically. So a variable velocity model. But ultimately, if you use the migration, you're just getting a velocity model out by which you can then collapse your energy back to the origin. And once you do that, then you know that the model's are right. Then you use those velocities to calculate depth. So it's all about getting depth. One of the advantages of migration, you'll see this when you do your reflection seismics, is it tends to take diffraction patterns. So that might look like a target, but that's actually a discontinuous layer, and you can see how that actually completely disappears, and you can actually see the continuity through the layer over here. So that's in seismics, that's more, that's the type of thing that you would use migration to get that information out. Whereas in radar, this is the information that we want to get out. We want to get the velocity model between the surface and the target.
So,
Sorry?
on the next diagram after migration, is that data been stacked or just migration such thing?
No. I understand your question. It's not stacked. It's not CMP stacked or bin stacked data like seismics, because your receiver, your transmitter and receiver are coincident. They're next to each other, essentially on top of each other. Whereas with seismics, you'll have your source, your transmitter is over here, and you'll have multiple receivers. Here you've only got one transmitter, one receiver. So the data is not stacked from a seismic point of view. So it's not like common midpoint stacking or something like that. But what you have done is you've stacked multiple of the same data set or the same line. So this might be, let's say, 1,000 traces from left to right here. But to get this data, we may have sampled this 8 million times. I think 8 million traces to build this 1,000 up here. So it's stacked from a noise filtering point of view, but not from a bin point of view like seismics. Does that answer your question?
Yes. And last thing, does it involve 3D or it's just 2D?
Okay, yeah. So it's not true 3D because your transmitter and your receiver are coincident. So you don't get move out. You don't get move out between your move out across your data. But you can create 3D models using it by putting together multiple 2D profiles or 2D time slices, basically, like this through the data. So you take multiple of these parallel to each other, and you can put that through, and then you use software to interpolate between two adjacent traces. And the software will then say, okay, I see this target in the one profile, and I see something that looks very similar. I'm going to try join them, essentially. And you can create a 3D data cube like that can be sliced and diced and worked with. But you have to bear in mind that, of course, the only real data you have is this data. The rest is a computer's interpretation of what it thinks the data in between should look like. So you always got to bear that in mind. So you would always come back to this when you were doing the interpretation. You might look at the 3D data cube, but if you wanted to get an accurate depth, you would always come back. You would find a trend in the 3D data and come back to the 2D data to look at the actual profile and look at the values that you're working with. So yeah, it has software on board to allow you to build a 3D survey quite easily, and I'll go through that a little bit later. Right, so that's basically just the basic radar theory. Just some applications in terms of how versatile radar is. You can use it for mapping roads to see the quality of the roads. This is a railway ballast. Stones underneath the railway here tend to get fouled up and that, and you get sinkage, and the railway lines start to buckle and warp or whatever. So you can.
On the one on the back of the car, are they measuring between those two, or?
No. So those are both. That's two different antennas. That in this case, they can be the same frequency, but one will be one of these is a 1 gigahertz antenna, and one is a 2 gigahertz antenna. And so the one this one only measures to about 20 centimeters depth into the tar, into the road, and this one will measure about 40 centimeters. And so you use the two as if they were next to each other, on top of each other. So yeah, so they're not. It's not it's not a CMP survey. You're not transmitting there and receiving there.
You're really only measuring a narrow strip of it.
Yeah. So, but it's still more representative than coring, because coring they'll go and stick a core every 50 meters or 100 meters. Then it's like a borehole. This is to coring what geophysics is to drilling boreholes. We try to fill in the gaps between the boreholes. So, and anyway, that interesting thing is these radar systems like this one now can do these at rail speeds at 100 plus k's an hour. So that's an interesting application. Ice thickness mapping, because of the hydrogen bonds in ice. You can actually get down to about 4 kilometers with an antenna like this. It's the only material that you can do that. This one is they're actually measuring ice thickness there, and that's to find crevasses so they don't drive the snowmobile into a crevasse. That's what a crevasse looks like, by the way. You can see these, as I said, so you get a discontinuity here, and you can see the diffraction patterns. So you get these half hyperbolas coming off of them. This is just contaminant mapping. You can see undisturbed layer of soil here. They've put in some landfill here, and it's leached through into the ground below. This is an interesting one. One of my clients mapping meerkat burrows in the Kalahari. That's not the data, by the way. But he was mapping meerkat burrows for a movie. They wanted to put cameras down and photograph them. Biomass calculations, these are roots of trees. You can use radars to work out how good the root structure of trees in a forest is. Are you planting optimal spacing? Pseudoconductivity maps for soil mapping for precision agriculture. So do you add more nitrates to soil? Do you adding something, so you can see where the conductivity of the soil changes. Does it relate to your production? And then stuff more that I guess we are interested in, geotechnical mapping, or mining hazards. You can see the antennas to get, that's the other thing I didn't mention is, as your antenna frequency decreases, the antennas get physically bigger, because to generate a long wavelength you need a bigger antenna. So you can see some of these antennas get fairly large. And you can use them for, this is the type of thing that you would get down to about 25 meters with. You can use it, this is in Namibia, finding gemstones in vugs underground. This is another customer of mine doing exactly the same thing as this. This is in the Namib, yes, I think Spitzkop or somewhere like that.
Is that in granite, the gemstones?
No, it's not in granite. It's in just below the calcrete layer. When you if you go to Spitzkop and everybody, you dig for tourmalines and stuff like that. That's exactly what these guys are doing. I don't know. This is actually underground, but he's using exactly the same method, but only interested in because it's only economic for him to dig down about 2 meters. More than that, it doesn't matter. The bugs are too small, unless it's something huge, of course. But sorry, I see this. Yeah, this is from Canada. So this is This is an underground working. I think they found gemstones, tourmaline, yeah. Okay, this is in our bushveld mines have a problem with domal structures, these potholes, these paleo potholes. If you mine through them incorrectly, and this is probably what you were looking at, this type of thing. If you mine through them incorrectly, they become unstable and you have rockfalls basically. So the idea is to scan the hanging wall. This is an inverted section, so that'll be your hanging wall here, and that's you'll be scanning up into the hanging wall. And basically you're looking for discontinuities in your structure. Boulder mapping, if big excavation, you say, again, you can't tell the density of this, but you can tell it's different to the soils around it because it doesn't contain as much moisture, so boulders like that stick out. Archaeology, this high frequency, that's looking for, that's a 400 megahertz antenna. This is what you were watching earlier on, concrete scanning. This is the biggest use of these things. So that's the same cart as you have. You've got just a much more advanced controller and an antenna inside. You can see subgrade collapse here. You can see pipes in a trench. You can actually see the trench itself over there. Oh yeah, it says security. This is in Gaza. They were looking for tunnels underground. Forensic detection. This one over here, they found the guy's wife underneath his new pool deck, so he went to jail. This is finding clandestine, or actually not clandestine graves, but unmarked graves, historic graves. So that's a big industry in South Africa now, believe it or not. Because of all these developments like the Dane Ferns, these gated communities have to do this type of stuff if there's any hint of historic graves. And then of course, I made the slide before it came out, but the new rover on Mars has a radar system in it. Not one of ours, I don't think, but anyway, this is just to see if it was feasible, what it would look like or something like that. But as I always say, put the Earth first. All right, that's it. So I'll leave this slideshow with you guys. And you can take a break now, I guess, for a few minutes, and then we can...
I'm still going to put some stuff together.
Yeah, I'll put the rest of this together for you.
Okay, so let's clap. Yeah, thank you, Terry.
I'm sure I'll switch that off.
No.